let's get right into it because I have a long way to go and a short time to get there. I have a lot of slides to get through. Shout out to my former student who's going to be speaking here soon, Victoria. So Victoria is a student since she graduated over 10 years ago, 12 years ago. So, but still a very trusted confidant, and I contact her all the time. We talk about biology and all the time. So let's just get right into it. This is a new talk. Some of it's old, but some of it's going to be brand new. I've not shown these slides before. If you've seen me give this talk before, a lot of it has been talking about nephas and ketones and hypocalcemia, a little bit like Jose was talking about yesterday, and how I don't think those three are necessarily causing problems. So essentially, this is kind of a summary of that type of slide, or that type of talk, is that high nephas and hyperketonemia and subclinical hypocalcemia are oftentimes thought to cause problems, and frequently this is the nutritionist who gets the blame, right? And I think this is due to one of two things. These are just simply metabolic adjustments that very healthy, high-producing cows will employ to make milk, or they're a consequence or reflection of a cow that's sick during the transition period and not eating well, okay? And everything in today's talk is going to be in this review. If you're interested in Journal of Dairy Science, my two co-authors are Aaron Horst and Sarah Kavidra. So, what is the traditional dogma about the transition period? Well, immune suppression is centered on that. Is that nephas, hyperketonemia, and hypocalcemia are causing the problems. Okay? I underline and bold this word here. So the global dogma of the transition period is that the cow calves, she becomes hypocalcemic, she has high levels of nephas. This, in theory, causes ketosis, which we know this isn't a one-to-one relationship. Importantly, these three are supposed to cause a reduction in feed intake, which then contributes to the DA. And here's what we're going to talk about today. These three supposedly cause immune suppression, and now that she's immune suppressed, she has an increased likelihood of developing some type of transition cow morbidity, right? And also they contribute to infertility and ultimately decrease farm animal productivity and farmer profitability. Okay, why do we think this? Why is this such a strong global tenet, right? Well, because there are hundreds of experiments and papers published in North America and Europe and Asia and South America that associate and correlate these changes in these three with negative outcomes. I just listed a few here. These are all very good papers. But there are many scientific papers that do not show a relationship between these three and a negative outcome. And it turns out, I think almost all healthy cows have high levels of nephas and ketones after they give birth and become mildly hypocalcemic. So I think it's dangerous for us as scientists to take a metabolite, boil it down or distill it down and think, okay, I'm going to diagnose a disease based upon a change in one of these simple metabolites. So the incidence of health problems is highest in the first month of lactation. I'm not doubting that. I'm not claiming that that's not true. Everyone would agree with this. The largest change in energetic metabolites, glucose, nephas, ketones, acetate, hormones like insulin, glucagon, epinephrine, cortisol, minerals, not just calcium, zinc, iron. The changes in all of these things, the largest swings in an animal's lifetime, from the day she's born to the day she dies, the largest changes is going to be in a very narrow window of time. So now mathematically, we're going to be able to correlate them with anything, right? So there's a lot of moving parts, and I think we, as an industry, then have assumed that this correlation equals causation. So, and then if we assume this correlation equals causation, then it causes farmers, or causes us, to recommend to farmers that they need to spend money on fixing it. And I think these expenses most of the time are unnecessary. So again, causing is here I just really want to emphasize that we have long believed that these things are causing problems. And you get then advertisements and models made like this where hidden ketosis causes infertility, less milk, culling, RPs. Well, if a farmer sees this every month, and I get the same dairy monthly magazines that you guys get, They see this every month for the last 35 years, 40 years, right? Well, of course, then if you see this enough, well, then you're going to spend money to try to fix this. Recent came out a couple months ago, a paper talking about global losses, economic losses in dairy cattle diseases. This probably came across your desk. And then it was picked up by the popular press, the cost of the world's top 12 dairy diseases. This was just a couple months ago. Subclinical ketosis, $18 billion is what this publication is. Now, this is mostly, I don't know what percentage is, but a very large percentage of this would be subclinical ketosis, hyperketonemia. Okay. My point of that slide is this is a very, very strong belief in academia.
Can you stop for 1 minute? Your microphone is reaching your cheek and it's making sound.
It's a little bit laggy.
Oh, okay. Have you not heard a single word I've said?
They heard everything.
Crazy American just babbling up there.
And the camera crew asked if you want to just put on that screen. They can see it.
Okay. But this is my good side. Okay. Davi, I get a couple extra minutes for the 40, okay? Okay, where are we at here? Okay, if this was real, right, and these are all very good scientists. I'm not casting aspersions. They're all very good people. But if this was real, we should be able to fix it by intervening. If hyperketonemia and high NAFAs and subclinical hypocalcemia were in fact causing diseases, it would make sense then, if we intervene and fix the problem, that health should get better. Fair enough, huh? Okay. So in the United States, we have these NOMS reports. It's every animal agriculture industry does it. It's an assessment of animal health in the poultry and beef and dairy, pigs, blah, blah, blah. So I just took the liberty of looking at some different culling reasons on the far left column. In 1996, 2002, and 2014. What do you see about these changes in culling? They're not changing, right? Despite the fact for at least 25 years now we've been aggressively treating post-calving hypocalcemia and aggressively treating ketosis. So, arguably, health is not getting any better. Maybe we're medicating the wrong things. I don't think you need to be a professor to sit back and say, hold on, we've just spent billions of dollars in the last 4 decades trying to fix these problems, and the problems aren't getting any better. Maybe we're spending unnecessary money. Okay, so the question then was biological plausibility. Javier talked about this yesterday, right? Mother Nature is rarely wrong. She's rarely wrong. She doesn't screw up, unless there's a disease. I'm not talking, lactation isn't a disease. Getting pregnant is not a disease, okay? Why would evolution favor a scenario where the mother, all mothers, not just cows, humans, mobilize adipose tissue, bone, and muscle to support lactation, and in the process of doing so, this would increase their chances of getting sick, because if she gets sick, her likelihood of feeding her baby now goes down. You know, so why would Mother Nature, our evolution, do that? I think there remains very little evidence suggesting NEFAs, ketones, and calcium are causing the disease. And the best line of evidence is extrapolated from the role in immune suppression, and that's what we're going to be talking about for the rest of the seminar. Okay, again, I'm not suggesting that health isn't an issue in the transition period. It's clearly a bottleneck, a headache for nutritionists and dairy farmers all over the world. This is a 1999 paper written by Jim Drakely. 50% of the cows get some of these problems. And of course, these problems occur in the very early lactation. Jose Santos wrote a very similar paper in 2004 out of California. I think it was 44% of cows have some type of negative outcome. The question I have, though, is, you know, of course, the dogma is that these problems here are caused by immune suppression. But of course, if hyperketonemia shouldn't be listed as a disease, well, now this number goes way down. If subclinical hypocalcemia shouldn't be listed as a disease, well, now this number even goes up further. I guess what I'm trying to say is I'm not really sure we're that bad. Is the dairy industry that bad where 50% of the cows get sick in the transition period? I have doubts. Okay, let's talk about this risk, these problems, right? The risk of dying in a plane crash is 1 out of 7.7 million flights. But the risk is 0 if you don't fly. My point here is metritis, for example. Clearly, metritis is only going to happen in the first week of lactation. She's not going to get it any other time of her life, right? You're not going to get metritis at 300 days of milk. You're not going to get metritis when you're a 10-month-old calf. So I just think there's a variety of issues. You're not going to get mastitis, well, you could, but it's very unlikely, right, before lactation. I think these are, DAs. DAs are most likely to occur in very early lactation, the dietary shift, or she's sick, she's off feed. So my point here is that I think we're assigning too much health problems to the transition period and this immune suppression. Okay. I would be very surprised if we took away hyperketonemia and subclinical hypocalcemia, 50% of our cows are sick. That's not a sustained. I think oftentimes academics, including myself, we're alarmists, right? We've got to scare you into thinking or paying attention to the rest of the talk. Okay, so let's now talk about, very quickly, the transition period of inflammation. The transition period, there's Erminio Trevisi. He is a professor in Italy. He's the godfather of this area, someone I admire very much. He's a friend. He has done a fantastic job of describing inflammation in the transition period. And now we know this actually starts to dry off. Dry a cow off, there's a 10-day window of inflammation following that. Then you got a pen move and all these things going on. Where's the source of this inflammation? Well, the mammary gland is an obvious source. The uterus and we think the GI tract is a source. So clearly there's a heightened risk of being exposed to an antigen in very early lactation. Where does this come from? Well, like I said, the primary sources are the mammary gland, the uterus, and GI tract hyperpermeability. There is also a thing called steroid inflammation, which I'll describe here in a minute. We oftentimes characterize inflammation by measuring acute phase proteins because cytokines are highly variable, they're very temporally finicky. So we use these acute phase proteins, which I'll show you in a minute. But if these barriers, if these epithelium become compromised and allows LPS, lipopolysaccharide, it's everywhere, by the way. This is a component of gram-negative bacteria, so it's on your table, it's on your phone, it's on your teeth. It's everywhere, right? It's ubiquitous. That's fine. It's completely through an animal's GI tract, but if the barrier becomes compromised of any one of these, now it gets taken up by LPS binding protein, chaperone to an immune cell. On this particular example, it's a Kupffer cell in the liver, and you end up getting inflammation. And serum amyloid A, haptoglobin, and LBP are the ones that most scientists measure just because they're, 1, cheaper, and 2, less variable. Okay. So this, on the left, is haptoglobin on the y-axis of 2 different experiments. This is a nice experiment because all they did was simply take blood samples throughout the transition period, okay? And then when they got to 100 days in milk, they retrospectively classified them. Are cows either healthy, right? They had no diagnosed disease, mild disease, severe disease, and the purple is they were either sold, meaning they were culled, or they died before 100 days in milk. So if on the 95th day of milk they died or got sold or left on a truck, they got assigned to the purple group. My point here is that at 2 days in milk, there's a huge increase in inflammation, right? And this inflammation then far precedes them leaving the herd. This same thing on metritis. She's inflamed long before she presents herself with the disease. So let's go back and then take a look at these different types of inflammation. There is sterile inflammation. For example, parturition itself, the act of actually starting parturition requires inflammation. Getting rid of the placenta requires inflammation. And, of course, uterine involution requires inflammation. These are all inflammatory events. So, most of the time people think of inflammation as being pathogenic, caused by some type of pathogen. So this is not the inflammation I think we need to worry about, right? Inflammation that's associated with a pathogen is what I think need to be concerned about, because sterile inflammation does not reduce feed intake. Let's back up a second. When you talk to dairy producers, right, what's the one thing they always say about transition cows? If I could just get her to eat, if I get her to eat, everything will be fine. Well, why isn't she eating? The number one thing that reduces animals' intake across the animal kingdom is immune activation. The cricket, not even mammals, if you cause a cricket to be sick, it'll stop eating. This is the inflammation that's associated with reduced feed intake. This is the inflammation that we want to counter and control. Anyway, so you get this immune system suppression models built like this, and this is just something I grabbed off the internet. You could find hundreds of them. Right? You have negative energy balance, leading to ketosis. This all causes immune suppression. That causes this, blah, 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 blah. So, and of course, if this is true, well, then we're going to spend money on trying to fix it. So, immune suppression. As far as I can tell, this is the first paper that describes it. A couple of people named Hill, Shears, and Hibbett in the UK, they talk about how there's a reduction in somatic cells to the mammary gland in an early transition cow when there's mastitis. Lloyd comes a couple years later in 1983, and I think he's the first person ever to use the word I can't even say the word transition cow immune suppression. I think he's the first person to coin the term immune suppression. Okay, again in the UK. But the person who took that dogma or that early tidbit of information and just ran with it and did a fantastic job is a guy named Mark Turley in Ames, Iowa, at the USDA, National Animal Disease Center. And his group just did a fantastic job of characterizing a variety of problems with the immune system through the transition period. There is reduced leukocyte effector functions like oxidative burst, its ability to cause cytotoxicity. Delayed leukocyte recruitment to the gland is really what they did a great job. You cause mastitis in a mid-lactation cow and a late lactation cow, and sometimes there's less somatic cell counts into the gland, or somatic cells, neutrophils primarily, during an infection in early lactation. Okay? And so, that's just from the Lloyd's paper. So, how do we characterize immune suppression? Well, here's what Curley and others have done. You take a blood sample 14 days prior to milk, for example. 2 weeks before calving, you take a blood sample, you take it back to the lab, you run some type of ex vivo assay on the white blood cells, and you get a measurement of functionality. Then, after calving, same cow, you take another blood sample, and you run the same assay again. And then, after she's out of the transition period, she's 30 days in milk, you take the same cow, another blood sample, take it back to the lab, and sure enough, around here, right, they appear less functional. And we know cows are more likely to get sick in early lactation. The white blood cells don't look as good in early lactation, so we're going to connect the two together, and it makes sense, right? They're more likely to get sick. This data is real. This is probably the reason why they get sick. Okay. Is this a fair comparison? Is it really apples to apples? Okay, here's what we know now, what they didn't know then. We know now that inflammation signals to the bone marrow to release more neutrophils. Okay? But remember, in 1980s and 90s, we didn't even know transition cows were inflamed. We had no clue that transition cows were in the midst of an inflammatory state. Okay? And this is just, and by the way, when the bone marrow releases a neutrophil, it is immature. It goes through a process of maturation while in blood. The key component here, it has to get this one protein called L-selectin, doesn't matter. Once it finally gets old enough to get this protein, now it can leave and enter into a tissue. But until that happens, it's immature. So inflammation causes the bone marrow to dump out all these immature neutrophils and aren't ready for the fight. Okay, so we've put this together in like a little cartoon. So this is pre-calving. And this box here is supposed to represent the circulating blood pool. And the blue is a mature neutrophil with L-selectins gets ready to invade into a tissue. It's mature, it's ready to fight. The green is an immature neutrophil. But before calving, vast majority of the circulating white blood cells are mature. Okay? So if a blood sample is obtained before calving and you take it back to the lab, everything looks great. Now she calves. Okay? She calves, and where do we have a problem? We have a problem with the gut, the mammary gland, and the uterus. So now, functioning mature neutrophils leave the circulation, and they go to where there's a problem. And that problem is, like I said, those 3 different tissues. And she's inflamed. So the bone marrow says, hey, I have a problem. I have to release more neutrophils. I got to fix this problem, right? And now in circulation, we have an enormous amount of immature circulating neutrophils, right? You take a blood sample now, take it back to the lab, and like, oh, there's a problem. These are not as functional as they should be. And this is how I think the foundation of this immune suppression idea. But again, the scientists in the 80s and 90s, they didn't know that cows were even inflamed, and they sure as hell didn't know that inflammation causes the bone marrow to release more circulating neutrophils. Okay? So how do we really study the immune suppression or the immune system in general? Well, we typically use mid-lactation cows, right? There's a consistent milk yield and feed intake. From a university perspective, there's a broader pool of cows to choose from. And of course, there's much less variability in the physiological, metabolic, and inflammatory basal state. So, but there's obvious limitations to using a mid-lactation cow. Clearly, the metabolism is very different. The immune system's status supposedly is very different. And of course, in early lactation, the mammary gland wants to make milk. And this is key to this whole issue, is that in late lactation, right, when she's 200 days in milk and you cause her to be sick, by that stage, her calf is presumably, to the stage where the calf could survive on its own. Right? But at 20 days in milk and she gets sick, she's still got to make milk. Right? Her priority is, okay, I want to fight off my pathogen, but I also still want to make milk. So that's a big issue. When you cause a mid-lactation to be sick, the mammary gland just gives up. Okay. So our group and many others uses the mid-lactation cow to assess the immune system. And here's just a bunch of papers that prove that. Okay. And it's been valuable. But what we wanted to do is, okay, let's go back to apples and apples. Let's compare the immune system of a very early lactation, not very early, 20 days in milk versus a late lactation cow. Head-to-head, okay, head-to-head comparison. And our hypothesis was that the transition cow would be more tolerant to LPS because it had presumably just been exposed to LPS in the gut and the mammary gland and the uterus. So it would be less sensitive to LPS in early lactation. And we have 2 papers that just came out in 2024, the spring, and this is the data I'm going to be showing you, and it'll be the first time I'm showing you this data, or anyone this data. Okay, the experimental design is quite simple. We collect baseline data for 7 days. We give the cow an IV, this is important, an IV bolus of LPS, which of course a cow would never receive an IV bolus of LPS, right? And then we compare early lactation and mid-lactation cows. And we also included some pair-feeding because we wanted to separate out the effects of going off feed, which I'm not going to talk much about the pair-feeding models because that was kind of boring. Okay. So moving forward, on the left axis will be rectal temperature in hours or time relative to the LPS administration will be on the x-axis. What I want you to pay attention to is the early lactation cows given LPS will be in the open triangles, and the mid-lactation cows given LPS would be in the closed triangles. So the LPS caused a fever, just like we would totally anticipate. But surprisingly to us, the cows that were in early lactation had a much more stronger febrile response, over a degree centigrade. Okay? Which kind of surprised us a little bit. And this is where it started to really get surprising. These are cytokines, TNF-alpha, interleukin-6, IL-10, were all more increased in early lactation compared to mid. Surprised us a little bit. Obviously, it was against our hypothesis. And then chemoatactic cytokines. These are the cytokines that are made within a tissue or resident immune cells that recruit neutrophils or other immune cells to an infected tissue, right? And again, all of them increased in early lactation compared to mid-lactation. And we took a look at acute phase proteins, same thing. The early lactation cows have a much more robust increase in LPS binding protein and haptoglobin. And again, against our hypothesis. We took a look at circulating leukocytes, in particular neutrophils and monocytes. When you cause an animal to be sick, white blood cells will migrate to a tissue. We presume this is prior to the LPS. We give the LPS, and they almost go down to zero. In other words, the white blood cells and this neutrophils migrate into a tissue, probably the gut. So then the bone marrow recognizes this large decrease in circulating neutrophils. There's inflammation, and it starts kicking out neutrophils again. And the early lactation cow's bone marrow is better at it, much better at it. And the same thing happens with monocytes. Okay, and then immune activation causes hypocalcemia. Jose was talking about this a little bit yesterday. Early lactation cows, you cause them to be sick, there's a larger decrease in circulating calcium. Okay, LPS caused the fever, cytokines, and this is all more robust, augmented in early lactation. Our hypothesis could not have been more wrong. You know, I'm not kidding when I say every single metric we evaluated of health was stronger in early lactation than it was in late lactation. Okay, what about productivity? Right, so this is feed intake and milk yield. This is the mid-lactation cow. You cause them to be sick. The early lactation cow goes off feed hard. She goes off feed substantially more than the mid-lactation cow. 68%. But look at milk. Milk yield on the first day looks a little different, but overall milk yield in those first 3 days following immune activation was not different. So despite the fact that the early lactation cow has this really strong immune response, she goes off feed hard, she still makes milk. That's what I was referring to earlier. That mammary gland, she's got to make milk, right? She's got to take care of her infant. And how does she make milk? Well, she does it with very different profile in the endocrine system. The mid-lactation cow has a huge insulin surge after the LPS. This is well described now in multiple species, but the early lactation cow doesn't. Remember, insulin is not our friend in making milk. You don't want high levels of insulin. And there's a huge glucagon response in early lactation. Collectively, these two are there to help the liver make glucose. Of course, the mammary gland needs glucose to make lactose. Lactose drives milk yield. And they also then have differences in non-certified fatty acids. In early lactation, they continue to mobilize adipose tissue during immune activation, but in late lactation, they do not. And the same thing happens a little bit in ketones. Go down, but they're still different than the mid-lactation cow. So from a metabolism production perspective, LPS markedly reduces feed intake, even much more in early lactation compared to late, but milk yield is not different. And the similarity in milk yield is allowed to occur because of changes in insulin, glucagon, nephas, and ketones, and glucose. Okay, so that was IV IV LPS. Never happens on a farm. So we wanted to create a model that's more reflective of on-farm infection. Okay, so we did intramammary LPS. We take LPS, inject it up the teat canal. She actually doesn't have mastitis, but the body thinks she has mastitis, okay? And this is this paper here. Again, it's a just a few months ago. Because of time, I'm not going to go through it all, but you just have to trust me. If you don't trust me, read the paper. Every single thing we measured in the IV experiment that were different in early versus late occurs in a more natural mastitis model, okay? So, the students just put together this little summary slide. Everything I've talked about here in the last 20 minutes, the early lactation cow, its immune system is amped up, it's ready to go, right? It is certainly not, from my opinion, suppressed. I can't imagine how you could look at all this data and say, yeah, that suppression theory is right. Okay, and this just came out a couple months ago. In fact, Victoria sent it to me, I think. It was you the one that sent it to me. Mucosal immune responses in transition dairy cattle. Contrary to previous reports of systemic immune suppression, the bovine mucosal response appears to be intact during the peripartum period. And there's another quote if you want to read that one down here. So my point here is that I think there's multiple scientific groups working on the same, or questioning the same thing. Almost every immune system variable we measured was more robust, but despite this exaggerated immune response, she still made milk. And the only way she can make milk in the face of reducing her feed intake is by mobilizing adipose tissue. The high NEFAs aren't causing her to be sick. It's a consequence of her not eating during a time frame where she needs to make milk. So maybe if it wasn't for this super strong immune response, morbidity would even be worse. Remember I told you that 50% number? Maybe it would be 90% if it wasn't for the fact that she was a champion in this little window of time. So if this is correct, what are we doing? Are there implications to how we balance rations? Certainly there's large implications to management, right? And again, I'm not suggesting that inflammation isn't a problem. But there's on-farm practical things I think we can use to help. It's like, maybe we're right. For example, you're probably familiar with Restore. And Restore was launched by Elanco a few years ago. How many? I don't know, 5 years ago now, right? It's bovine granulocyte stimulating factor. It causes the bone marrow to make more neutrophils. In large part, it didn't work very well. Right? Well, I think now we probably understand why it didn't work very well. They're not immune suppressed. Transition cows, are you familiar with this bird flu going on in the United States at the moment in North America? It is freaking everyone out, right? This bird flu is a problem, and it's migrating north. If it's not in Canada by now, it will be soon. Turns out, though, that the early lactation cow, the transition period cow, is essentially immune to getting bird flu. And there's 3 different reports here, from one of them's from the USDA, that document this. Hold on. If the transition period cow is supposedly immune suppressed, you would think they would be the most susceptible to bird flu. Transition cows are the least sensitive to heat stress. They bounce back quicker. You'll see in my next presentation, I think heat stress is essentially an immune activating event. And the effects of using NSAIDs in early lactation are highly inconsistent. So I think there's a variety of really non-scientific things that we can extrapolate. Hey, this whole transition cow immune suppression thing needs to be reevaluated. So this, again, is the traditional belief. Right, I've already showed you this slide, so I'm not going to belabor it. But I think we need to think of it differently. Because we're suggesting that farmers spend money on fixing these problems. Oh, by the way, I'm not suggesting that a pre-calving calcium strategy is not important. Clearly, you have to have a pre-calving calcium strategy to prevent milk fever. I'm talking about the boluses afterwards. That's what I'm talking about. Okay, I think these are a consequence of immune activation-induced low feed intake during a very specific window of time. She's sick, but the gas pedal is still on making milk. Okay? So I think these are reflections, they're symptoms of prior immune stimulation. So here we have different immune activating events. I should have heat stress up there. Anyway, leaky gut causes an inflammation. Now, for time, I didn't go into, well, I did show you a little bit of hypocalcemia and immune activation. reduces feed intake. I didn't show you about fatty liver. The Florida group has just done a fantastic job of describing how LPS impairs fertility. Now we have this contribution to DA. Remember, at the same time, she's trying to make milk, so that's why she has high NEFAs, and you get ketosis. On this particular model, right, where would you, as a consultant and talking to a dairy farmer, where are you going to suggest he spends money? At the bottom of the figure or at the top of the model? At the top. This is where money and resources need to be spent at preventing these things. It's not the nutritionist's fault. So I think this makes sense. It doesn't make sense for there to be immune suppression at the most important time of her life. She's got to take care of herself, obviously, but maybe even more important to her, she's got to take care of her baby. These shifts in leukocyte functions, I think they're on purpose. They're not an accident. And if you want to read more about it, this is the review to do so. I think they're just simply a reflection of an animal that's already in the midst of an immune activating event. For example, if I take John and I take his blood cells, take some white blood cells from him, measure the functionality, right? He looks great, he looks healthy. Then I give him a shot of LPS. 6 hours later, after I give him a shot of LPS, I take his blood again, take it back to the lab. His white blood cells are going to look dysfunctional, even though he's in the midst of a massive immune response. That's why they look dysfunctional, because they're in circulation. All the good ones are in his arm, where I put the needle. Okay. I don't know, how am I doing on time, Davey? Where's Davey at? How am I doing on time, John?
6 minutes yet.
Oh, do I?
We give you the 45, but if you're done,
Well, I only have one more slide. I'm surprised I even practiced this morning. I'm surprised I went through that so quick. So let me try to show you maybe more of what I'm talking about, okay? So the cow gets some type of immune activating event, okay, in the transition period. Obviously, this causes immune activation. That's what it is. And this immune activation causes infertility. There should be word causation here. And it causes hypocalcemia. And it causes decreased feed intake. Okay? Now this decreased feed intake, at the time that she's trying to make milk, I'm really stressing this because a late lactation cow just gives up milk. You cause her to be sick, the mammary gland gives up. But the early lactation cow, the mammary gland doesn't give up. So now she has a reduction in feed intake. This obviously causes a reduction of body condition score. You'll hear people talking about, well, if they lose more than 8/10 of a body condition score, things are going to go to hell in a handbasket. Well, yeah, but it's not the loss of body condition that causes the problems. The loss of body condition is a consequence of not eating. It's just energetics 101, and we talked about this last night. Okay, so now the decrease in feed intake causes her to have high NEFA. This causes fatty liver. This causes hyperketonemia. What we've done then, now these are all correlated with the problem, with the immune activating event, and we've taken this to the bank. In other words, we've said, okay, this instead of actually being correlated, this causes. We now have to fix these things. We have to spend money fixing it. And I'm saying we need to spend money, but not at fixing these things. We need to spend money at preventing these things. So, appreciate your attention. I don't think I saw many sleepers, so I appreciate that. And I don't know if we have time for questions, or we just go in.
Yeah. Well, what we'll do is actually have one question.
Okay.
First come, first serve. But I want to remind everyone too, if you didn't get a chance to use that QR code and put your questions there, write them down, and then before we do the roundtable, you can put it on that app. Okay? So who's got the most urgent question in the audience? Chantal here?
Thank you. This is excellent lecture, actually. for the after calving, can we manage the intake of the cows, to join the herd mate? Should we focus on energy density or dry matter intake, having all these factors, hormones and lactation hormones and other affecting this issue? Thank you.
Yeah, that's a great question. Of course, people have been working on appetite control for a very long time, right? And there's all sorts of elaborate hypotheses why some cows don't eat well after calving, right? And like I said, this is something every dairyman in the world will say, I just got to get her to eat. And I have a small brain. I think small things. Feed intake is the most sensitive to immune activation. Every one of us in this room has been sick and recognizes the consequences of being sick to your appetite. So, how do we get her to eat more? Prevent her from getting sick. I know that's a small, is it raining again? It is, yeah. I know that sounds like, that's a flippant answer, but I think it's the most simple answer is typically the one that's most correct, likely to be correct. Prevent her from getting sick, and then she will eat.
Thanks. Okay, Lance, you're up again for a 30-minute talk, talking about zinc hydroxychloride effects on biomarkers of inflammation and intestinal integrity during feed restriction and heat stress. So changing topics slightly.